what I mean.
Okay, so today we're gonna do induction.
Oh.
This is the best thing in the whole wide world.
That scares me.
Don't be scared.
It scares me when you say this is the best thing.
Well, what?
Oh no, what happened?
No. I love doing proof by induction because it just like.
Yeah, I don't know about this.
So here's the thing. I normally feel pretty good about class, and when we get to induction and like I can read a room and tell that we're ready for it. I have a fair amount of concerns. I'm gonna be honest. I don't know if it is that there are not very many of us, if it's how you're sitting, or if it is that we've been inconsistent for like the last month. I don't know what it is, but I feel like we're not ready. And I don't know, like, I don't think I'm doing a worse job than I normally do. I don't know what's happening with my English, but like. So it may just be that I'm reading it wrong, and I know it's not.
I don't feel fine about it.
Well, and it might be that you're the loudest one in the room, and you don't feel fine about it, and you just made gagging noises about learning induction, which you know nothing about. That might be what it is. So we're gonna do our best today, but I didn't want to do it in Zoom because I need to see your faces. And I was at a talk over at this conference where the person was like talking about like a flipped classroom and basically like allowing your students to struggle, right? He said, I realize that I am very selfish as an instructor, and I want to be the one to see them figure it out. So, and I was like, I'm that same way. It's hard for me to leave stuff for you guys to do on your own because I want to see you do it. I want to see the light bulb happen, because those light bulb moments are the reason I continue teaching. And if I never saw those, I wonder if I would just quit.
That's just what you keep saying.
So, what we're gonna do today is proof by induction. Now, we're gonna sort of, this analogy is how I like to teach this, about ladders. So everyone imagine a ladder. There's a ladder here, yes? You see it, okay. Now, the idea about induction and how we do these proofs is you're gonna like say we can get on the ladder. We can reach the first rung of the ladder, yeah? And that's point number one. Point number two is that once we are on any ladder rung, we are able to step to the next one. You tracking what I'm saying? So number one, we can get on the ladder. Number two is once we're on any rung, we can get to the next one. Yeah? Knowing those two things means you can get to any ladder rung you want. Do you believe that?
Yep.
If you can get on the ladder at all, and once you're on any particular rung, you can step to the next one, then you are able to get to any ladder rung that you want. That's proof by induction. We're gonna prove these two things and then say it's true about all of them. Say this, whatever property it is works for everything because these two things are true. You good? Okay, so if n is a positive integer, setting that up, I was ready to do the rest of this. Oh, who knows? Just share the screen. Right. So, I didn't track to see if y'all actually watched the video, but I assume that you did, right? Because y'all are 300 level math students and you're fine, right? I did put it on YouTube this morning, so if you didn't get the link or whatever, it's there. What?
Like the Zoom links.
Yeah, you like the Zoom links? Okay, so the this idea here that you have n is a positive integer, adding up the first n positive integers, you could figure out by just like doing it, or you could also just do this, which is kind of cool. That thing over there is what's called a closed form. This is a closed form. When you only need to know what number in the sequence or whatever that you're on. This side is a summation. Are you seeing that? This is the sum of the first n integers. So you're gonna start your indexing at k equals 1 and go up to n. So that would be when k is 1, that's 1. When k is 2, that's 1 plus 2. When k is 3, that's 1 plus 2 plus 3. I mean, when n is whatever. When n is 4, that's 1 plus 2 plus 3 plus 4. We tracking this? Yes. So this is the sum of the first n integers. And eventually what we're going to prove is that you can, instead of doing this summation, you can actually just do this. And that is powerful. That's a powerful tool because you don't have to do everything, you know, you can just plug in your n to this and you're good to go. Now, the other way, if we couldn't do induction with this, we would like have to prove this for every number forever. And that's not reasonable to do. So what we are going to do is induction. So I kind of hate the way our textbook does this, but this is sort of the notation for it. I don't want you guys to be writing P of K and P of K plus 1 because I hate it. I hate the notation. You can look at your textbook to figure out what's going on, but like, this is confusing. This makes a get on a ladder, be on a ladder rung and get to the next ladder rung. This makes that really complicated sounding. But this is what it is, that P of n is a statement defined for all integers in A is some fixed integer. Suppose the following two statements are true. P of A, you can get on the first ladder rung. Yeah. And then number 2 is that at once you're on any ladder rung bigger than A, then you can get on the next one. Yeah. Okay. So that's what all of this is saying. Then the statement for all integers greater than A, P of n is true. Here's another example. You have an infinite row of dominoes. Yeah. To know that all of the dominoes are going to fall, what are 2 things that have to happen? The first one needs to be pushed over. And beyond that is that every pair of dominoes is close enough that once this one knocks down, it knocks the next one down, right? Yeah. So the first domino falls, and if a domino falls, the one behind it falls. Yes, that is the principle of mathematical induction. Okay, so that's a lot of words. Here we are with the base step here is to show that you can get on the ladder. And then the second step, the inductive step, is that from one rung, we can get to the next one. Do you spell a ladder rung with a W? I don't think so either.
No, it's just
My
RU.
brain wanted to do it really
Is
bad
that
just
when
now.
I rung out,
Yeah,
that's W.
yeah. Okay, so basic step is that you can get on the ladder or you've knocked down the first domino. The inductive step is, okay, well, let's say we can get on a particular ladder rung. Can we get to the next one? Notice how this has an arrow in it. This is a P implies Q statement. This is an if then statement. We're going to assume this thing, we're going to show this thing. Right, this is an implication. This is a P implies Q. Now, this is a valid proof method. We kind of just talked about it and y'all believe it, right? So the first ladder rung falls and 1 will knock down 2. So you get that 2 is knocked down, right? And the second ladder, you're on the second ladder rung, 2 will knock down 3. I'm mixing my metaphors. No one's knocking down rungs on the ladder. The second domino falls. Here, this is that the second domino falls. We also know second domino falls and second domino will knock over the third. So the third domino falls. This goes on forever, right? This is modus ponens. infinite number of times, right? P implies Q, therefore P, right? Q implies R, therefore R. We tracking? Okay. This is, I'm just putting this. Okay. So what we're gonna do right now is find a formula for the sum of the first in odd integers. And then we're gonna prove it. A formula, by that I mean like a closed form. Yeah. So let's practice. Let's work. So when n equals 1, the first in odd integers, this is a 2k plus 1. We're going from k equals 1 to n. We good? This is the sum of the first in odd integers. An odd integer looks like 2k plus 1. K is going to start at 1, and we're looking at the first however many odd integers. So if we're looking at just the first odd integer, I need to start at 0. I need to start at 0 to get n equals 1 to work. I just broke my brain. Let's use a -1 and then I don't have to do that. Let's use 2k minus 1 and go from 1 to n. That'll work. That'll do it. I got it. So the first odd integer is just 1, right? We don't just, oh, gosh. Okay, the first odd integer is just 1 and we're adding up the first one odd integer, so that would just be 1. We good? How about the sum of the first 2 odd integers? That would be 1 and 3, which is 4. The sum of the first 3 odd integers would be 1 and 3 and 5. That is 9. Yeah? Are y'all with me? Okay, I confused myself and everyone else when I did this thing, but whatever. The first 4 odd integers would be 1, 3, 5, and 7. That is 9 and 7 is 16. So a like formula or a closed form for this would be where we could just like plug in the in. Can you see a way to do that to get the sum of the first in odd integers without having to add up a bunch of numbers? Anybody see a pattern happening in these numbers? Well, most of math is pattern recognition. Do you see a pattern there? Those are easy to see with that highlight on there.
Like squares.
Perfect squares of what, Charlotte? Yeah. Of n. Yeah. So the sum of the first n odd integers is n squared. Crazy, right? Whew. So what is in the sum of the first 5 odd integers? Should be 25. 1 and 3 and 5 and 7 and 9. Heck, it is 25. It works. Yeah. Okay, so this is 1 plus 3 plus 5 plus dot 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 plus this would be a 2n minus 1 is equal to n squared. Now I'm doing this to get here, if I'm on like the third odd integer, I want 5, not 7. Do you get what I'm saying? So when I plug in 3 here, this would be 6 minus 1, which is 5, which is the third odd integer. Yeah. Yes, if I made that 2n plus 1, I would be going to 7, which is actually the fourth odd integer, not the third. Yeah?
Yes.
Okay, so shifting that a little bit so that we so that the indexing makes a little bit more sense. Okay, so this is written out without the summation notation, but in closed form looks like this. You could also write this left-hand side as a sum, as that sum that's circled up above there. So k equals 1 to n of 2k minus 1. I mean, if you do n equals 1, you're going from 1 to 1, so you're looking at 2 times 1 minus 1, that's a 1. When n equals 2, you're looking at both k equals 1 and 2, so 2 times 1 minus 1 plus 2 times 2 minus 1, that's 1 plus 3, which is 4. You get what's going on there? How the summation notation is working? Yes? Okay. If you did n equals 3, you would have 3 pieces that you're adding together with the k equals 1, k equals 2, and k equals 3 cases. Okay. So we are going to prove now that the sum of the first n odd integers is n squared. This is going to be our first opportunity to do mathematical induction. Okay, so when we do induction, remember we've got to get on the ladder. So we need to get on the first ladder rung. That's the base case or the basis step. Or does the first domino fall, right? This is the question that we're asking ourselves. Does this work for the very smallest of n's? Right? So n equals 1 is where we have to start. You're with me on that? The sum of the first n odd integers. So we're going to start with the first one, right? So we're going to let n equal 1. Is 1 equal to 1 squared? Right? This is 1 plus 3 plus 5 plus plus 2n minus 1. Does this actually equal n squared? That's the thing we're proving. Yeah. Or if you're using summation notation, you're going to go from k equals 1 to n of 2k minus 1. That's equal to n squared. Now, you're going to do the base case is for the smallest n that we can use. Can we get on the ladder? Does it work for our smallest possible value? Yeah, n equals 1. We're summing up the first one odd integer. That's 1, just 1 by itself. Is that equal to 1 squared? Yeah, it is. So we're good to go. Yeah. Okay, so your base case holds, and then you've got to move on to the what's called the inductive step. This is the thing where if you're on any particular ladder rung, can you get to the next one? So we're going to assume we're on the ladder, and we're going to show we can get to the very next ladder rung. Yeah? Okay, so we are going to assume for some k that is bigger than or equal to 1, right? That n equal to 1 was our smallest possible n value, right? So we're going to assume for k bigger than that or equal to it. We're going to assume for some k. Should I use k? If I'm using that notation, no. Unless I change these to i's. But you don't have to do both of these notations, just pick one to use, yeah. So if we assume for some k greater than or equal to 1, that this works. I'm going to do the this one for now. You don't want me to use the expanded thing? I would imagine that this would be this is a whole lot more abstract than this, which is why I was doing it. Is it not? Yes.
I'm used to that.
So we have 1 plus 3 plus 5. Now we're going to the kth one. So we're going to do ... plus 2k minus 1. And we're going to suppose that that is actually equal to k squared. So what we're assuming is that this works when we're on the kth ladder rung, right? And k is 1 or bigger. Yeah. This is the thing that we get to assume. This is the P part of that number 2 point. Assume you're on a ladder rung. Can you get to the next one? So does this work for K plus 1? That's what we have to prove. So we want to show that 1 plus 3 plus 5 plus 2K minus 1 plus 2K plus 1 minus 1 is actually equal to K plus 1 squared. Because of the orange or because it's too small? Better? Better? Yeah, this looks weird. This is these are the first K terms, yeah? Well, I'm replacing the K with a K plus 1. That next one is 2K plus 1 minus 1, right? Just that thing that's inside of there, but it does look awkward. But like this is a term by itself and this is the next one. So you got the first K terms and then the K plus first. Yeah.
Why is it on the other side of the equal sign, it's K plus 1?
That's the thing we're trying to show. The sum of the first n odd integers is n squared. So the sum of the first K plus 1 odd integers, that's these many, should be K plus 1 squared. The idea is that this number here matches this number. The sum of the first n odd integers is n squared. So the sum of the first K plus 1 odd integers is K plus 1 squared. We get to assume, after we show that we can get on the ladder, we then get to assume for some K that is greater than or equal to that basis step that works. And then we're going to show it works for the very next one. Okay. If you're using the summation notation stuff here, which perhaps would be easier to read, I don't know. This is going to be the sum from I equals 1 to K plus 1 of 2I minus 1. But that is equal to K plus 1 squared. Or if you're using it here, this is the summation from I equals 1 to K of I, 2I minus 1, I mean. That is equal to K squared. Like I said, I don't care which one of those that you do. Obviously, for like coding purposes, one of those is nicer than the other. But that requires you to understand it, so. I don't know. All right, I'm gonna write a proof now. You good? I know I haven't actually done anything, but I'm just gonna do it in the proof. Okay. We will prove by induction that the sum of the first n odd integers is n squared. For the base case, let n equal 1. Notice 1 equals 1 squared, so the base case holds. Every time you do a proof by induction, you have two things to prove: that you can get on the ladder, and once you're on the ladder, you can get to the next ladder rung. All right, so we are on the ladder, yeah? Or we have shown that we can get on the ladder. This is left-hand side equals right-hand side, yeah? Now, don't say this part if it's not obvious, you know? Like 1 = 1² is obvious, but you're actually, this is the thing you're trying to prove, so don't say it's equal before you're showing it's equal. Does that make sense? Students always do this thing where they're like, this is the thing I want to show, but then they like just say it. Well, that's not showing it. That's just saying it, right? So be careful about like what you're assuming here. Okay, so n = 1, the sum of the first one integers, that's the left-hand side of the thing we're doing, that's 1, and the right-hand side is 1², so this works. Now we're gonna do the inductive step. So for the inductive, this thing, when you do the assumption part here, that's called the inductive hypothesis. Good science. So the inductive hypothesis is the like, hey, if you're on a ladder rung and it works, that's the inductive hypothesis. So for the inductive hypothesis, suppose for some k that's bigger than our base case or equal to it, that this is true, right? So that the sum of the first k odd integers is k². So that 1 + 3 + 5 plus ... plus 2k - 1 is actually equal to k². For those of you who are itching to use summation notation instead, you're gonna write, you know, I = 1 to k of 2i - 1, that is equal to k². I don't know how to make this look just slightly different, but not be in orange so that Logan can read it. Maybe, is this orange better? Okay. All right. So we want to show this is true for k + 1. Yeah. Consider, oh, that's the wrong color. So, for those of you who are counting, I am right there. I'm writing the left-hand side down. Yeah. What am I definitely not going to do right now? Write that part. That's the thing I'm trying to show. I cannot write that down. Do not write that down. Don't do that. There's this void in here. That's the proof. Yeah. Don't put these things next to each other until you have shown it. Yeah. That's the thing that we want to show. Don't write them next to each other yet. Do you understand me? Okay. They're not equal yet. We don't know that. That's the thing we're trying to show. What can we do though? In what way?
2 times k + 1, and then you get 2k + 4, and then you have -1, so you have 2k.
Huh? Is this what you said? I'm simplifying this. No?
I was simplifying that, but then I was also adding it to the other one.
Yeah, but why shouldn't I do that? I know something about this.
Something about that.
What do I know about this?
It's K.
Basically. Oh, so added to K squared.
That whole thing is K squared. Uh-huh. K squared plus two K plus two minus one. Yep. This is from the inductive hypothesis. That's where we pulled that thing, that K squared. That's where it came from. Yeah. And then simplifying this guy, we're looking at two K plus two minus one. Yeah. Everybody's with me, or you're not with me at all?
With you.
With me?
I like
Sort of.
factoring, it's fun.
So K squared here, then plus two K plus one. Everybody with me now? I should probably have some equal signs around here somewhere. Okay, good. Maybe I should move these. Y'all don't get mad at me. You just sit. No, I'm just gonna leave them. I'll leave them. I'm leaving them. What's that equal to? And what were we trying to make it equal to?
K plus one squared. We did it.
We did it. This is K plus one squared. Good.
Number one stuff too.
I think you probably did.
No.
Gotta get rid of that guy and put a different color in here now, this one. Okay, so if you're doing summation notation here, this is the sum from I equals 1 to K plus 1 of 2I minus 1. This is equal to the sum from I equals 1 to K of 2I minus 1 plus the sum from I equals K plus 1 to K plus 1 of 2I minus 1.
If we're not doing that notation now, will we eventually have to?
No, you can get around it. Sometimes it's gonna be nicer. If you are continuing in math classes, then yeah. You should probably get used to it. So, but splitting, I mean, it makes sense, right? This is the first K plus one term. So if I put K of them with this summation, then I have just the K plus first left. Yeah. If it would make more sense, just don't put this part here, put this guy. Right? But the idea is that you're separating this into the thing you know something about from the inductive hypothesis. So this right here is K squared. Yeah. Again, from the inductive hypothesis, this thing is K squared. And then this is just the K plus first term. So you're just looking at this. And then that gets you to K plus 1 squared again. So you're going to say something like this. Thus, the inductive step holds. And we have shown that the sum of the first in odd integers is n squared. Box. I look at this and I get kind of overwhelmed because there's a whole lot of colors happening there. I don't think I was overwhelmed while we were doing it in the moment. I know that I wasn't, but like looking at it now is very overwhelming. The colors are intended to help you. The pink is showing you where things came from. The yellow is to make sure that we know what we're doing. We're trying to make the left-hand side look like the right-hand side. We don't know that it is yet. We're trying to prove that. We're going to use the inductive hypothesis, the stuff that's underlined in pink, to get us there. The summation notation that is in the orangish color, that is optional, or you can do the blue stuff. Do you have any questions about that? Okay, does the idea also make sense? Okay, ready to do another one? Okay. The sum of the first n positive integers is n times n plus 1 over 2. Not even squared, just I.
Side.
Yeah, so we want to show, the idea here is that we show that the sum of the first n positive integers is equal to n times n plus 1 over 2. Or if you are doing this, you would do 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 over 2. That's the sum of the first n integers, yeah? Not odd, not just positive, yes? Are y'all with me? Okay, so this is what we're trying to show. The first thing that we should do is prove it for our base case. So prove we can get on the ladder. What's the smallest n value that we have? So when n is equal to 1, well, the sum of 1 is 1. So we're going to test is 1 times 1 plus 1 over 2. What is that? Yeah, it's 1. So base case works. So we are going to assume for some k greater than or equal to our base case. So 1, greater than or equal to 1. That 1 plus 2 plus all the way up to k is equal to k times k plus 1 over 2. So now what we want to show here, like this is big picture, want to show, this is what we're actually doing in the proof. We're going to do 1 plus 2 plus up to k plus 1. But that's actually equivalent to k plus 1 times k plus 2 over 2. Right, k plus 1 for the ends. Tried to write this before, but I think I got distracted. So this is the n equals 1. This is when n equals k, and you want to show it when n is equal to k plus 1. So I replaced the n's here with a k plus 1 and a k plus 1 plus 1, which makes a k plus 2. Yeah? Okay. Give me the first sentence in my proof, somebody.
We will prove by induction that the sum of the first n positive integers is n times n plus 1 over 2.
What's next?
For the base.
Notice 1 times 1 plus 1 over 2 is equal to 1. So the base case holds. What do you want to do now? So for the inductive hypothesis,
Suppose for some k greater than 51.
my brain stopped working. Sorry, hold on. Ready now. Suppose
Suppose for some k that is greater than or equal to 1, that 1 plus 2 plus 7. K times k plus 1.
now we're doing the considering for the left-hand side of this thing, right? That we're trying to make look like the right-hand side. In between here is where the proof is. Yeah, okay. What do I actually know that this is equal to? That's from our inductive hypothesis, right? We have the sum of the first k terms is k times k plus 1 over 2. Then we've got that k plus 1 other thing just sort of hanging out. Now here is probably where you should do some like arithmetic off on the side instead of trying to do it in the middle of your proof, because now my task is to make this look like this. So I gotta get a common denominator, do some simplifying, do some factoring. Right? So I'm gonna, break away here and do some of that. So I have k times k plus 1 over 2. I'm gonna make this then plus a 2k plus 2. I multiplied top and bottom by 2. Right? Yes. If I multiply k plus 1 by 2 over 2, I would have 2k plus 2 all over 2. So now I have a common denominator. But things are not right still. So actually, I'm looking at this. Are we tracking that? Oh, which is the thing that I need. Those Ks do look bizarre. They're getting worse. Oops. This is the kind of proof where I always want to do, y'all have seen Legally Blonde? I know this sort of ages me, but you've seen Legally Blonde? Where at the end when she's giving her speech and she goes, "We did it." This is how I always feel when I'm writing this final sentence that summarizes everything. We did it. That's how I feel. The inductive step holds, and we have shown which is much less exciting than saying, we did it. And we have shown that we did it. Yeah.
Use that circle box.
That's what the W to the fifth is, which was what was wanted. I think you can count that as we did it. Yeah. Looky here. All right, the inductors opposed, and we have shown that the sum of the first n integers is n times n plus 1 over 2 blocks. W to the fifth. We did it.
I feel like the length of the proofs are like longer now, but like it's not that hard.
Yes. Yeah, it's gonna be no more stuff. So the like logic part's coming easier, right? And the rest of it's just sort of along for the ride for now. But you're right. I mean, I think so too. I guess we can't say if you're right. I gotta shrink things in to fit here. All right. The logic here is pretty intense though, but I'm glad that you're like tracking what's going on. Do you have any questions about that one? Questions?
So, that's where you said after it says consider the sum in the following and all that next line, I don't understand where you got the thing after the equal sign in the very next line.
This is from the inductive hypothesis. This thing. Is this thing.
What's the equal sign?
It's right here. What I'm looking at is this thing plus a thing, and this thing plus a thing. The thing is this thing. Right, because I'm looking at the k plus 1, first k plus 1 integers now, but I know stuff about the first k one, so I can replace that with this. This k plus first thing is just hanging out.
Okay.
All right, how are we doing? We doing good? Okay. No? Okay, good. That's good. What things would show my age? Don't say that, because don't say. Okay, whatever, I'm 34, it's fine. This is a fine age. But I was talking to someone about it yesterday. It's really strange to me that Taylor Swift and I are the same age. And that feels wrong.
Does it make you feel young?
No. It makes me feel like I'm ancient, or that she's really immature. I'm not sure which one. But like, that's mean. I get that.
Wait, you feel like you're older than her,
Oh, absolutely.
but you're not.
No.
So that should make you feel young. It makes you feel old for your age.
Yeah. Yeah, like I'm in my life, my choices are very different. Mhm. She like swallows a sip of water and right, she swallows a sip of water and it is more than I make in a year. Like, you know, I don't know, in 6 years.
You don't write love songs about your ex and make millions on
I don't, and I wouldn't. But yeah,
Missed opportunity.
I
know,
know,
right?
I know. What was I thinking? I chose poorly.
Just family.
I chose a family and this career, if you can call it that.
Was, like,
Yeah, I did. And I would do it again. Hmm?
Did you watch Grey's Anatomy?
I watched some of it. It got weird after a certain point, and I just didn't have, I did not have the, yeah, if we're in like double digits of seasons, I'm out. You know?
I only got to like season 18.
Oh,
Oh,
the fact that there are 18 seasons is bothersome.
Only. I was surprised by it to be an only. The
Yeah,
only
yeah.
that threw me off.
How many episodes are in the season?
Like 20 something.
And they're like 45-minute episodes, right? Oh, it's so much.
Yeah, I guess I can't, another show I watched, it's like 13 seasons, I watched it like twice.
What
through.
show?
It's called Supernatural, I watched it twice
I
through,
love
like,
Supernatural, but I couldn't get that far. I got to season 9.
oh yeah, it gets terrible at the end, but I had to commit.
When I
I'm
was on
like, the
maternity
third
leave,
time.
I watched all of Rizzoli and Isles and Bones. Different maternity leaves, yeah. Mhm. One was Rizzoli and Isles and one was
What
Bones.
is Bones?
It's a TV show. She's I don't know how to describe it.
Okay, I'll look it up. Let's see.
She's yeah. Mhm. She helps solve crimes with the
okay.
FBI. It's
Oh, I
fun.
like
It's
this
a good
one.
show. Okay, so sometimes we're not gonna do things with summation notations and it's not gonna be about that. It's gonna be about things like this, which was really fun. And here's the like, this thing is actually kind of challenging and a place where you get to be really creative, which is crippling for some of you and will be really fun for others of you. But we're gonna prove that n factorial, that's n factorial, is less than n to the n for all integers greater than 1. Like, we get to do real math now.
Oh, that's not what I'm here for.
Hey, what are you here for? But like, really, what are you here for?
To fulfill my degree.
What's your
What
degree?
is this?
Cybersecurity.
I didn't have. Do you even know, have you even know glasses?
What classes are you in? I'm in
Never.
procedural right now.
Oh, okay, so you're behind.
I'm
Whoa,
taking object
Oh, wow.
oriented in the summer.
I-
I see.
ugh, cannot,
It wasn't.
I
hate,
died
it was-
in that
It was just
class.
the observation.
That's where I said, nope, not gonna be a cybersecurity major.
Wait, in Java, that's where you? Okay.
All integers greater than 1. So where should we start for our base case?
1, 2.
She was so confident. 1, no, I take it back. It's 2. Okay, we're gonna let n equal 2. Do you know what 2 factorial is? Oh, you don't know what a factorial is?
Sorry, I just said,
One time-
because Bruce
one-
is math major. I
it's
figured you
1
would know.
plus, it's 3.
No, it's not. Marina is correct. It's 2.
It's 2, what?
Sorry, I trust,
Prime Factors?
Nope.
Or something?
I
No,
trusted the
it's
math major.
1 times 2.
Marina's not a math major.
No, I trusted
Oh,
Bruce.
oh,
and
yeah.
it was
Oh,
wrong
don't.
answer. That's what I'm saying.
2 factorial is you multiply it like all the way down. So 3 factorial is 3 times 2 times 1.
Oh.
6 factorial is 6 times 5 times 4 times 3 times 2 times 1.
You know, like, it's been a long day.
All right, so 2 factorial is 2. That's this side. What is 2 squared? Nice. So notice that 2 is less than 4. So the base case holds.
Oh, 2 is less.
Notice that when I do this, I am not going to put those together in one inequality until I have done it. You get what I'm saying? We're not going to write, notice 2 factorial is less than 2 to the 2 and then do stuff. Don't do that. Don't do that.
Oh, so you put the answers in?
Well, just wait.
Just-
Just wait. Please. Okay, for the inductive step, what are we going to do? Oh, don't all of you yell at me at once, please.
Okay.
It is.
Assume for some.
Okay, is greater than or equal to 2. Good. We're going to assume it works, right? So we are going to assume that k factorial is less than k to the k. So the inductive step, you assume it works for the kth step, right? And we're gonna show now that it works for the k plus first. What?
Is it K squared or K to the K?
That's a K. If you can't tell what it is, it's a K.
I thought it was K, but I didn't
Looks
know
like
that
something
that's what
foreign,
it
it's
is.
a K. Is it because you write it weird? Do you do the line then a C whenever you write a K?
I don't like a C, it's a V.
Oh, okay, that would explain.
How am I supposed to write a K?
Just do it like one stroke.
What?
Or
That's an
like-
R.
That's an R.
Well, it's not my fault you're.
Marina, how do you make a K? Everybody else does it right. We Americans do it wrong. So tell me how we make a K. Yes, you learned from Americans how to make a K. Never mind. Stupid question. But how do you make a K?
I go like this. and then-
There's like 17 strokes in your K.
No, that's how I do it. She does it the right way.
I think we should use my handwriting as a basis for.
It's way better.
I don't understand. Oh, boy.
Beautiful. I've never
Beautiful.
seen a better K in my entire life.
I know, right? Hi, Alessandro.
How do you
Okay.
write your K?
Yeah, Alessandro, how do you write a K? Do you do it like this?
No, that's wrong.
Y'all, how do you write a K? Marina writes 45
Oh,
things.
do they do like the whole? Or like. it's
That's
like
an
a-
R.
It's like a weird, like, bubble thing.
Yeah, I don't know. I don't.
Oh my God.
I kind of do like that. I'm not
Yeah, that
gonna
looks
lie.
much
I do
better.
like the
You know,
little
when I
bubbles.
first tried, that was so good.
Yeah, I like the bubble.
Okay, now it's starting to seem
That looks like a
It
star.
looks like a star.
This is actually what's happening. I'm not picking up my pen and it's doing that
We're
thing.
proving K.
Okay, many of them. Okay, so we are on we've done our base case. We have gotten on the ladder wrong. We are saying we can see that 2 is less than 4. We are gonna assume it works at the kth step. So assuming that k factorial is less than k to the k, and now we know what a factorial is. And so we can do this. We're gonna show that k plus 1 factorial is less than k plus 1 to the k plus 1. Oh, I wish I had fit that all in that one space. Ruth, what is happening with you right now? What are you exasperated about? No time like the present. Okay, so we have, we are trying to show that k plus 1 factorial is less than k plus 1 to the k plus 1.
Like see this little piece right.
So how?
I'm just so confused.
Well, I haven't actually done anything yet. Right? I mean, it's a base case, but we're not confused about that.
No,
What are we confused about?
because I thought that the factorial was always like the fastest growing thing.
Presupposition is.
The fastest growing thing for what? Well,
It's faster
exponential
than-
growth is exponential growth is exponentially faster.
I think the K messed her up.
I'm confused about what you're saying, I guess, is what. This is messing with ideas that you thought you had, which about the factorial was wrong and even more wrong when the factorial is just adding, not multiplying, right? Okay, so let's fix that, but let's move into what we're actually doing here, which is trying to prove that k plus 1 factorial is in fact less than k plus 1 to the k plus 1 for all integers greater than 1. So this is, should we just like write the proof and then do this later, or should we do it here? Guys, my son lost his first tooth last night.
Oh my God. Tooth fairy?
Tooth fairy visited, yes.
How much money is it?
$2.
Oh,
What?
nice.
Is that too much or too little?
Too much.
The tooth fairy and the tooth fairies had some discussions. Like the tooth fairies really locking themselves in
Were
the,
there 2 tooth fairies?
Mhm.
Like they didn't
Right, that one did, no.
They got it mixed
Just
up.
like-
That Toothfairy thought like, should they,
Very important.
should they get, they've got 20 teeth, these children, each of them. Right, well,
$40 right there.
for one of the kids, so should we just have $80 lying
Or you can
around?
just say the first two's worth double.
Yeah.
Everything else is
Oh,
more.
yeah.
Ooh, there you go.
Oh, yeah.
You can, you
Yeah,
can
they're
like
like,
switch
welcome
it up.
to. By the last two, it's 1 cent.
Yeah.
Yeah.
Or you can add a sales tax.
Teach them about exponential decay.
Teach them about tax.
Yeah.
You can tax them.
Yes.
Yeah.
So y'all, no lie, they're always competing with each other. My 5-year-old and my 4-year-old, everything's competition. And
course.
last night, about, I don't know, 15 minutes after Riley lost his tooth, Ellie said, "I have more teeth than Bubba."
I was thinking of something like.
She did, she's like, "Look, mine's loose." I was like, "No, it isn't." Well, let's hope not. If it is, something's wrong. Yeah, "I have more teeth than Bubba." Yes, good. Okay, so we're gonna start here. Remember, the proof is in here. We'll call this the pudding, and then we need to get to this part, okay?
Okay.
So I have k+1 factorial, which we now know what that is. It is k+1 times k minus 1 times k minus 2, all the way down to 1. Yes. Okay. Alessandra, do you know what a double factorial is?
I do. I'm sorry. I don't know what a double factorial is.
No, I was just asking. I didn't know until I was watching a Math Jeopardy thing. I was like, because I was thinking, do we
It
skip?
skips 2, right? So it's like k minus 2, k minus 4, k minus.
That's what I was thinking, but maybe that's not right. I thought it does skip every other one. Yeah, it's every other one. Mhm.
Where do I watch this Math Jeopardy?
I did it at a conference. It's like, yeah. Mhm. Okay.
That's what they do at conferences. We were wondering.
The
We were trying to
students,
figure it out.
the students,
Take us.
yeah, there were students competing. Yeah, you're right, I didn't take you. Do you know how much work it would be to get us all ready for Math Jeopardy? A lot.
I don't think I'm ready.
You might be. I am
Wow.
not. Okay, so k+1 factorial. Hi, Bryson. k+1 factorial. How do we write this? How do we use the fact that we know something about k factorial?
K times k plus 1 plus k plus k minus 2. Yep. Okay, yep. That's definitely how we do it.
You're almost there.
I was close. I was very close.
I think that should be right.
And then
Oh, no.
what I actually know is that k factorial is less than k to the k.
Okay.
Okay, so I'm going to substitute that in for the k factorial part and make that equality an inequality.
Okay.
Now I'm trying to get to a place where I have k+1 to the k+1. I am going to make this now I haven't broken anything. But if k is bigger than or equal to 2, then k to the k is always less than k+1 to the k, right? 2 to the third is less than 3 to the third. This is just facts, yes?
Whoa.
Hey, guys, how many k+1s do we have?
Okay. We don't know.
K plus.
Oh, is it?
Oh, we do, I know. Here's the k of them, and here's the another one. That is k to the k+1.
I'm losing
Right.
One of my students told me earlier that she wanted to be a teacher, and then today she heard me helping a student, and she thought, nope.
That sounds about right.
She was like, it was really painful to listen to you try to answer those questions. Mhm. Yep. She said, I don't know that I would have been patient. I said, some days I'm not. Okay, so, but this is the, we have, you said facts about me not being patient? Wow.
No,
Whoa.
I said Ruth's fault and she said facts.
Oh, that's fair. Okay, so, 2 factorial, we did this for the base case that, when n equals 2, this works for the inductive step. We assume it works on the case one, show it works for k plus 1. We just did that. Now we're gonna write it up nice and pretty. We got time. All right. Now, Whitney, you've sort of done the last 2. Daniel, you seem to be feeling good. Do you want to do it?
I shoot the first sentence.
Okay, I'm ready.
The start of the first sentence. We will prove by induction. That the impact order is less than into the n.
You did only give me the first half of the sentence.
For all energy. Great. And let's do the K2 thing
Oh, now you're ready. Ready.
for the base case. So that's it for the base case. Let n equal to. Notice. that-
Careful.
Oh,
I'm just telling you to be careful.
2 factorial.
Wouldn't need that middle step. We can probably fix everybody, but yeah, sorry, I'm sorry. Yes, okay, 2 factorial is equal to 2. Go ahead.
And that 2 squared is equal to 4.
Here's your opportunity to
So-
use clearly.
Oh, clearly
Good.
2 is less than 4. So the base case holds.
Or conversely, hurrah. When we get to the end of this proof, y'all surprise Alessandro and Bryson with what we were talking about earlier, okay?
Okay.
Okay.
Okay, ready to go.
For the inductive hypothesis. Ooh, I like that. Suppose for some k is greater than or equal to 2.
Induction is the right time to use suppose.
I actually heard her in the video. She started to write suppose and then she laughed and then she erased it and then wrote a suppose.
Every single
Yeah.
time she wrote something.
She kept writing suppose and then she'd erase it. She's like,
Well, I can't yell at somebody for something and then do it a whole bunch.
I'd like to see a suppose counter from that.
Yes, yes. You be in charge of that, Charlotte. Okay, I'm ready. Keep going.
that some k of that. And then will we put in the thing that we're trying to do in the work to show?
Not yet. So we gotta do the assumption first, right? Or the supposition first. Suppose that k factorial is less than k to the k. Good?
Yes.
All right.
Consider. Oh, yes.
Whew.
You know, it's the right next one.
Good.
The sum.
No,
Sorry.
because there's no sum
Consider
here.
fact or
K plus 1 factorial, good.
is less than k plus 1 to the k plus 1.
Don't do that yet,
Don't do that yet.
right? Because that's the thing we're trying to actually show. So don't do that there. You're gonna remember, you gotta do this part, proof, gotta do the pudding. And then you get to say the thing. Okay, so left-hand side, we did it. Now we actually have to prove it, and then we can say it.
So then. So then we equal to K, yeah, K plus one, the K factorial
Times K factorial, keep going.
is less than the K plus one. the K squared.
K to the K, those are Ks,
Oh, sorry, I'm lying.
No, it's my bad apparently, because I read my Ks wrong.
K plus one. To the one, say to the one. Times K plus one. to the K.
The one was just to help you, but I'll go
That's
ahead
what I
and
said, I
write
was
it.
very, I was like,
Well, because I asked you how many Ks we had, K plus ones we had, and y'all said, K, even after I wrote that little one. So,
equals K plus one to the K plus one.
good. That one is, these two are equal. Right? These two are, yes, both less thans, but because overall, so overall we have the less than, it's an inequality overall, yeah. You don't want to break this by going the other way at some point with your, because then things don't make any sense. So you want to either stay equal to or follow the same equality, less than or greater than all the way down through these things, yeah? So,
Wait, hold on, why is it equal now?
oh my gosh,
Look at the step above.
how many K plus ones do we have?
One.
It equals,
So
okay.
we used to think.
This thing is
Oh,
equivalent
okay,
to
okay.
this
So
thing.
usually, I'm used to when we do this math, I'm used to the equal signs or whatever being equal to the thing on the left. When we're doing it equal to the thing
Above it, yep. Yep.
That's what.
Yep. Yeah, we're doing this string from things like from one step to the next, but because we're working only on the right-hand side here, we're gonna get to say that the left-hand side is actually less than the right-hand side, because we're just messing with this side now.
Yeah, you go from like doing it from the side to like right above it.
Right.
I mean.
So that's why you wrote it as less than with the so.
Because we're following this string of inequalities down or whatever, and because at some point it's less than, we have to, then the whole thing is less than, right? But if you were to like switch that and go less than and greater than, like you wouldn't know what to do, there's no reason to do that, right? Yep. Okay, so you get this thing, which is actually what we were trying to show.
Hooray.
We did it.
Whitney, thank you so much. Oh my gosh, y'all said you were gonna do it.
Sorry, I forgot what we
I
were
thought
supposed
we
to
were
say.
gonna do it.
I thought there was
when we
more
were
to it.
doing
Yeah, I thought we were gonna
the
do it before the
I
box.
thought there was more to it.
Yeah.
You just proved the induction hypothesis. That's what I didn't say.
Actually, we didn't get to the box part yet.
Yeah, not the box.
Who said huzzah?
Say you, Charlotte. That was definitely Charlotte. Nobody else would say that.
Confirm or deny. Accusations against me.
Ready? We did it.
We did it! You have to do the little like,
And we're done with class now?
yeah, yes, we did it.
Can I take a picture?
Yeah, hang on. I need to see where we are.
One big proof.
So it's hard to write and prove at the same time.
Oh, it is, you're right.
It's
There you go.
Question.
Yes,
Are you gonna
ma'am.
do that thing where you don't want my homework?
No, I want your homework.
Okay, good.
Your homework's due today. I want your
Okay.
homework.
I just feel like every time I actually have it.
Yes, Charlotte, I want your homework. I'll take it. And I'll have your other homework. I haven't graded in here still.
Oh, all right.
See, it's your own fault that it was late, so it's on you.
Ooh.
Right.
Yeah, I mean, that's fine and everything. I just don't like that Blackboard shows that I have a zero.
Sorry about that.
Like if you.
And I will
just
make
hit
sure
it so
when I
didn't
send it
see
to you,
that would make
it's
me
all
happy.
in one file.
I'm counting off 15 points from a business calculus student who
So-
submitted a test in 5 separate PDFs.
Holy cow.
Jeez. I submitted one in 6.
That wasn't a test.
Hey, those days are behind me now.
I didn't want to be cool.
Anybody else have one to give me? I wish you'd found
I
a
got-
stapler, Charlotte.
I
don't know
thought
what
there was
happened,
like a
huh?
staple boy here, isn't he the
I
staple boy?
don't know what happened to it, someone stole it.
You're the staple boy, this is your
Oh my
choice.
God.
I literally have
Look at
staples.
guys, see if he's stapler.
Oh, okay, alright, we got a new staple boy.
Someone stole my staple.
I love the staplers, the staplers.
Here, I have a stapler too.
Have you ever seen one? No. The staplers?
I think test Thursday.
They like to put cuts
Thursday,
pages and
next
then
Thursday.
use them together.
We're moving this back one day.
It's kind of cool.
What do you tell
I got it.
I'm a glass country music on the way home.
Yeah.
Yeah,
you.
just do what you normally do.
Anybody else have homework? Anybody know you're all
Yeah.
on? Okay. Bye.
I mean,
Thank you.
why are you asking? Are you gonna think it's in your cup?
Just take a picture of his haircut. Isn't that,
show them?
yes,
Hey,
hi, yes.
I do the,
This, from this step to this step,
I guess.
why is it,
okay.
you go from this symbol.
We do
here
like
to
what
this.
the ones that's like really zoomed out. Of like the
Because
one.
this is less than this. This thing is less than this thing.
Okay.
Alright,
But
tell
this
them the
thing is
usual
equal
then,
to this
okay, got it,
I
that's what
mean,
it's called.
so my hairdresser, she
Rules.
uses, she doesn't even use scissors, she uses a razor. And she goes,
Oh. Oh.
cause she's a pro. And like, I don't know, she just like, has like a 4 on the sides, I guess, depends. I don't know, something like that.
Alright, you'll have to, okay.
When you have like bases,
I
you
wanna
have the
approve.
exponents, yeah, that's what's happening here.
Alright, well, thank you.
So the reason why we're using that is because of.
What? No, stay over there.
Stay over
Why
there.
don't you just pull down the screen?
It's not gonna work.
Here you go, Ruth.
Stop it. Yes, here.
What about it?
From there, but we use the symbols for here. Because you're substituting.
What symbols? They got names.
Don't test me.
Which symbols?
So we're substituting this right here, and then we're using the less than because we substituted. From there.
Yeah, so k factorial is less than k to the k.
Okay.
And that's coming from this, yes.
Okay,
And then this is, this step is just facts.
I mean,
right.
I guess another way. You did it like this because that's how you did the work. But another way is like, you can
Yes.
start with the assumption. So k factorial is less than k